Welcome to another work example. Today we're going to look at a problem in which we have two blocks which are connected by a massless rope and a frictionless pulley system, as presented here in the drawing. We're told to assume the coefficient of friction between the block and the surface is 0.4, and you're asked to determine what is the speed of the blocks after block A has moved 6 feet. Of course, there's a couple things that we want to return to with the discussions of pulleys and relative motion. And part of that is the aspect that if block A has moved 6 feet, what does that mean as far as block B? Similarly, what does that mean when it comes to velocity and or accelerations to these blocks tethered together by a single rope over a massless and frictionless pulley system? And what we can observe is any displacement of A in the x direction will equal the same displacement of B in the y direction. Similarly, as a result, the movement of A will equal that of B. Of course, this will be in the x direction, this will be in the y direction. But again, the directions as far as velocity and displacement and such are desirable is important if we return back to previous chapters. Here we're looking at conservation of energy. We're looking at work energy principles. Now we're told that there is friction. As a result of friction, we can acknowledge the fact that we need to first determine what exactly is the friction force, and then determine how much work is done as a result of friction. So first things first, we want to draw a free body diagram quickly of A. We've got a normal force acting upward. We have the weight of A acting downward. And I'm going to remove the W for weight. Just for preference, instead of using a W for weight, I'm going to return to using mass A multiplied by G. As an aspect that because we're going to be doing work energy principles, we're going to be using a W for work. So we have the mass A times G acting down. We have therefore a normal force. We have the tension. And we have a capability to say that we have a force of friction. So the normal force, if we do this, is equivalent to the mass times gravity. And as a result, we have a friction force that is equivalent to 0.4 multiplied by the normal force. So we find that the force of friction is equal to 0.4 multiplied by the mass A times gravity. So we have that this is equal to the 0.4. Again, that was our mu. Our static, our coefficient of friction. So we have 0.4 multiplied by the mass, which is 10 over 32.2. Since we're dealing in pounds, we're going to utilize US customary, so we divide by 32.2, we multiply that by 32.2. So we find that the force of friction is equal to 4 pounds. Now, what we want to do is now we want to express the fact of what is work. Well, work, if you recall, is equal to a force multiplied by a distance. So in this case, we have 4 pounds multiplying by the distance of 6 feet. So we have the work done is 24 foot-pounds, or pound-foot. So that is the amount of work that's being completed. And remember, it's a force of friction. It's in acting to the left, but if you also recall, by definition, force of friction is always treated as being a negative work. So in our case, we want to say that the force of friction is a -4. Therefore, we can plug in and we find that we get a -24 foot-pounds. Now, what else is going on in this problem? Well, if we're moving block A by 6 feet, that also, as I said, means that we're lowering the block B by 6 feet. In addition, we can acknowledge that the velocities must be the same. So let's go to now our definition equation. In this case, we're looking at a system particle. So we want to make certain that we are acknowledging that the energy of the system must be conserved. So even though work is only acting on A, B is tethered, and so it's actually working through all of the system. So here we have the work done is equal to the change in kinetic energy within the system plus the change in potential energy within the system. So we have this -24 foot-pounds. That's equal to 1/2 the mass. Well, we're going to have both masses. So let's put them both in. We have 10 over 32.2 multiplied by the velocity squared plus 1/2 times block B is only 5, but still we divide by 32.2, it's 5 pounds, so we need to convert to mass times velocity squared. Now, like I said, if they weren't tethered together, that we knew that the speeds were the same for both A and B, we'd have to put these in as separate terms, but we can acknowledge the fact that because they're equal, we just have a single speed. So we have this present. And then we have the change in potential energy. Now, the change in potential energy is an aspect that if A is moving 6 feet, B must also drop 6 feet. We can call this a B prime, and we could also say that we have an A prime that has moved 6 feet. So what we have, A hasn't changed in height, but B has dropped, which means we have a mass of B, which is 5 over 32.2, multiplied by gravity, 32.2, multiplied by the change in height, which is 6 feet. I'm going to switch this to listing this as a positive because here is where I want to acknowledge the change in height is a drop, and that's where the negative sign actually comes into play for our calculation. So what we now have is we have a -24. We have 1/2 times 10 over 32.2 times v squared plus 1/2 times 5 over 32.2 times v squared plus the 32.2's cancel out. We have plus a -30. So we have -24 is equal to 1/2 multiplied. I'm going to add the 5 and the 10 together, so I get 15 over 32.2 times v squared, combining the terms, minus 30. So we actually find that when we add these together, we got 30 minus 24 is equal to 15 over 64.4 v squared. And so I find that I have that v squared is equal to a summation of 6 multiplied by the 64.4 divided by the 15. And that gives me a v squared that is equivalent to 25.76. So from that, I can obtain that the velocity, or speed, I should say, is equal to the square root of the value, which gives me a moving speed of 5.07 feet per second. That is the speed that A is moving with to the right. That is also the speed that B is moving downward with at the instant shown. And so we can observe that this is our value. I'll go to 4 significant figures, 5.075 feet per second. Hopefully that clarifies and helps you with your understanding of power or of work energy systems where we have multiple bodies present.